Hey folks, my name is Kevin Arrangers. I'm the Executive Director of the Space Foundation Discovery Center in Colorado Springs, Colorado. And if you're watching this from home, you probably share my love of all things space. From the courageous astronauts that pilot amazingly powerful rockets into space, to the satellites, spacecraft, and rovers that explore distant planets and moons throughout our solar system, to the incredible images of the universe taken by both Earth and space-based telescopes. All of these things make my job super exciting by bringing the world of space to you each and every day here at the Space Foundation Discovery Center. So come along with me as we take a journey through our gallery. Today I want to explore two of my very favorite things that at first glance might seem very, very different. Motorcycles and rockets. Yes, folks, motorcycles and rockets. I have the pleasure of riding my motorcycle to the Discovery Center each and every day, and when I walk through those doors, I'm immersed by some incredible objects and artifacts from the history of space travel that are all around me. Like rockets. Now, I know what you're saying. Kevin, motorcycles are really different from rockets and can't launch me into space, orbit the Earth, or fly me to the moon. And you'd absolutely be correct. They can't. However, like all objects, motorcycles and rockets are governed by the very same laws of physics, whether they travel horizontally along a road or vertically by blasting off from the Earth into space. To better understand this, though, we must first look to Sir Isaac Newton and his three laws of motion. So come and join me in my garage workshop. Newton's first law of motion describes how an object acts when no force is acting upon it. So motorcycles and rockets will stay still until a force is applied to move them along. Likewise, once they're in motion, they will not stop until an outside force is applied upon them. Newton's second law says that acceleration occurs when a force acts on a mass. What that means is the more mass an object has, the more force is needed to move it along. A large rocket, for instance, is extremely big and heavy, much bigger than my motorcycle, and will need stronger forces to make it accelerate forward. And Newton's third and final law states that every action has an equal and opposite reaction. It's Newton's third law of motion that helps us to understand the similarities and the differences between motorcycles and rockets and the force that's used to propel them forward. And a great way to understand that force is to look closely at a key component that motorcycles and rockets have in common: an engine. That's right, an engine. One of my favorite artifacts on display in the Discovery Center is the Aerojet Rocketdyne RL10 rocket engine. I even love how that sounds. The RL10 was one of several engines that comprised the Saturn V rocket that took the Apollo astronauts to the moon and will also be used in the future as part of NASA's Space Launch System. I'm always amazed as to its size, its various components, its hardware, its plumbing, and most importantly, how it worked to accelerate rockets into space. Although you can't smell it at home, I sure can, and the thing even smells cool. Now, I'm sure as heck not a rocket scientist, but I do know a thing or two about motorcycle engines. For instance, this 1960s era Harley-Davidson twin-cylinder, piston-driven engine that I'm building right here in my home garage is a great example of how a basic gasoline-powered motorcycle engine, also known as an internal combustion engine, are designed to provide the force that powers my motorcycle down the road. This motorcycle engine, along with many modern motorcycle and automobile engines, still work on pretty much the same principles as they did when the first one was designed and tested back in 1876. Internal combustion motorcycle engines need three very important ingredients in order to create that bang of internal combustion. Those three ingredients are air, like what's all around us in the atmosphere, fuel, like what's contained in this external gasoline tank, and spark. Spark produced by ignition via spark plugs. Again, thus the name ignition. Without any of these three ingredients, an engine absolutely will not run, and thus will not be able to produce the power to accelerate my motorcycle forward. If you happen to be a shade tree motorcycle mechanic like me, air, fuel, and spark are your three very best friends. If any of those three are missing, your motorcycle absolutely will not start. And just ask me how I know that. Could it be air? How about spark? gotta be. Yep, it's fuel, no fuel. The story of an internal combustion engine begins with that bang inside of a very confined space called a combustion chamber, like the cylinder here on this Harley engine. The bang is actually a timed, controlled burn of a mixture of fuel and air. An internal combustion piston-driven engine like this Harley engine typically has 4 operations, which are called strokes. A stroke is nothing more than an up and down movement of this piston inside of a combustion chamber. And each of the 4 strokes has an action. The first of which is intake, or bringing the air and fuel mixture inside of the combustion chamber. The second is compression, or squeezing that air and fuel mixture together. The third is combustion, or the explosion driving that piston downward in the combustion chamber. And then lastly is exhaust, which is expelling of the spent air and fuel mixture out of something typically called an exhaust pipe.
Sounds ridiculously complicated, doesn't it?
Yep, it might seem that way, but I promise you, it's not rocket science. The great thing about a 4-stroke engine is when you stare at a drawing of one or an animation on, say, YouTube, you will begin to understand for the very first time the interconnection of all of an engine's components: pistons, rods, cranks, camshafts, valves, and yes, spark plugs. It's an incredible moment once you get the hang of it, and one that can truly inspire a lifetime in engineering or mechanics. Or for me, a wacky space museum director with a passion for these motorcycles and rockets. Let's now explore how a rocket engine works in order to launch our astronauts and heavy payloads of material and fuel into space. To do this, I want to introduce you to my esteemed colleague here at the Discovery Center, Lou Ramon. Lou was one of many talented and courageous engineers and technicians that made history by building rockets and training astronauts to travel to space and land on the moon. We may all dream of being an astronaut one day, but as we say here in the Discovery Center, no one goes to space alone. It truly takes many thousands of hardworking engineers and technicians, and not just those astronauts, to travel to the moon and beyond. So let's meet Lou Ramon, our rocket expert, to learn more about rocket engines.
Thank you, Kevin. To start off, let me tell you a little bit about myself and my background. Before I moved to Colorado and became a docent at the Discovery Center, I worked for almost 50 years at NASA's Johnson Space Center in Houston, working on almost all of NASA's human spaceflight projects, starting with the 2-person Gemini program and going all the way up through the International Space Station. During the Apollo program, I was lucky enough to be assigned to a 5-person team that reported directly to Neil Armstrong for Apollo 11. So I got to work with Neil, working with him on the lunar module in person, and it was quite an experience. Since we're going to be talking about rocket engines, let me just tell you, my first job at NASA was as a rocket engine test engineer, testing the small rocket engines that the Apollo lunar module used to maneuver itself in space. But that's enough about that. Let's get serious and start talking about rocket engines as well. In many ways, a rocket engine is much, much simpler than Kevin's Harley-Davidson engine. It has many fewer moving parts that have to work at just the right times to have it function right. Like the Harley, though, a rocket engine generally needs 3 things to make it work. First, it needs fuel. Then it needs something to burn the fuel. In the Harley engine, it uses gasoline for the fuel, and it uses air, or more specifically, the oxygen in the air, to burn the fuel. Well, in space, of course, we don't have any air. We don't have any oxygen, so we have to carry our own oxygen, or a chemical that contains oxygen, something that we call an oxidizer, with us. And finally, we need something to ignite or start the fire burning. And that's it. We don't need any valves or pistons to convert the chemical energy from the burning or fuel and oxidizer mixture into mechanical energy like the Harley does, because rockets don't turn wheels or propellers or paddles to move. In fact, obviously there aren't any roads in space to drive along, so we don't need wheels. All they do is throw out the hot gases from the burning fuel in the oxidizer. They throw them out through a particularly shaped engine bell very rapidly. And this action of throwing out the hot gases is what moves the rocket forward. Just like in the air, you might blow up a balloon. And when you let go of that balloon, the air that's been compressed inside blows out and moves the balloon forward. It's the same sort of thing. We call this push that moves the things forward the thrust from a rocket engine. Now, a rocket engine has only 4 main parts. It has the injector that squirts the fuel and the oxidizer mixture into the engine itself. Now, the injector looks a lot like the head of a shower that you have in your bathroom. Here's a picture of one. Now, some of the holes in the injector let the fuel come out, and the others let the liquid oxidizer flow through. And they have to be precisely aimed so the mixing is complete to make the engine burn evenly. If it doesn't burn evenly, it's not going to give us as much thrust, and in the worst case, it could even explode. Next, we need some way to start the whole thing burning. NASA uses an igniter, which is really just a fancy name for a spark plug, a lot like the spark plug in the Harley engine. And once that mixture is burning, once it starts burning and that spark plug fires once, it keeps burning until the fuel and the oxidizer are shut off, or you run out. Pretty simple. The combustion chamber is where the fuel and the oxidizer are burned together last. And lastly, the engine has an engine bell or exhaust, where the hot gases are let out of the engine and precisely aimed to move the rocket forward. That's it. Now here you can see an example of the rocket engine that we have at the Discovery Center, a simple rocket engine. The injector would sit on the very top of this, and the igniter would poke through just below that. You can see the combustion chamber where the fuel and the oxidizer, once they're mixed, are burning. And then they go through this nozzle and come out the bell at the bottom. And that's what guides the exhaust gases out through the engine. It's a lot simpler than the valves and spark plugs and pistons and cams and stuff like that that the Harley engine has. The trick with the rocket engines is to get all that high energy stuff to burn in a controlled and reliable manner without destroying itself in the process. Figuring out how to do that is what makes rocket scientists rocket scientists. Now at the Discovery Center, we also have an actual rocket engine that represented a major breakthrough in rocket design by being able to go further, faster by using a different fuel than what we normally use. We have a real RL10 rocket engine, and this was the first rocket engine that successfully used liquid hydrogen instead of a fuel like kerosene and liquid oxygen. In order to keep that fuel and oxidizer liquid, it's got to be kept very cold, close to minus 350 degrees Fahrenheit. Now, the thing that makes it unique is that hydrogen, the liquid hydrogen, has much more energy in it than the kerosene that was used in previous rockets did. So pound for pound, it can go a lot faster and a lot further than the older types of rocket engines. Now, NASA has used later versions of this RL10 engine for the top stage of the Saturn V rocket that sent astronauts on their way to the moon. And they used that same engine, just scaled up to be bigger, for the Space Shuttle program, and they're going to be using that same design of an RL10 engine for their new Space Launch System rocket, the SLS. Now, if you look at it, as you can see from the RL10 that we have on display, even though a rocket engine is much, much simpler than the Harley-Davidson engine and has fewer moving parts, there's a lot of complex plumbing and stuff that's needed to operate the engine and control it. After all, you got to realize you're controlling an explosion and carrying it with you through space. Now, one last thing I want to talk about related to rocket engines, and particularly related to the rocket scientists who design and build and test them. My last boss in Houston, a fellow named Lon Miller, worked on the space shuttle rocket engines in Utah before he came to Houston where I was. Now, I always considered him to be a real rocket scientist because he worked on rocket engines for half of his career. And he was talking to me one day about some of the most exciting things that he got to do with the shuttle engines. And he summed it up simply by saying, any day when you can go to work and see fire and flames and smoke coming out the back end of a rocket like it's supposed to, and there's a whole lot of noise going on at the same time, that's a really, really, really fun day. Now, Lon and I were lucky that we got to have a lot of fun days in our careers as rocket scientists and aerospace engineers. Maybe some of you will get a chance to do that too. Meanwhile, that's about it, all I have to talk about today, so I'll turn this back over to Kevin. Kevin, finish this up.
As you heard from Lou, rocket engines are amazingly powerful pieces of engineering. The thrust from a rocket engine can launch a rocket vertically and with tremendous velocity, much more powerful than my chopper back in my home garage. Are you inspired yet? I hope so. And it's my belief that you don't need to be a rocket scientist to understand the very basic physics and principles that are required to build an engine that power us down the road or launch us out into space. And like we said earlier, no one goes to space alone. It takes all of us to learn from one another, design and test new ideas, add a little bit of creativity and the elbow grease of trial and error to get anywhere in this world and beyond.
I hope you enjoyed today's lesson. If you want to learn and do more, please come back and join us here at discoverspace.org for additional classroom lessons and activities. And if you really love what we do, please consider making a donation to support our work or become a Passport member here at the Discovery Center. Once again, on behalf of all of us here at the Space Foundation Discovery Center, we'd like to thank you for tuning in and joining us. But before you leave, just like George the astronaut back here, if you're traveling in your rocket ship into space or you're riding your motorcycle down the road, please remember to wear all of your safety equipment, including your helmet. Please stay safe, and please come back and join us often. Thank you.